Okay, welcome back. This is the second video in the testing module, and today we're going to talk about, first is black box versus glass box testing. So far, what we've talked about is how it's really hard, if not impossible, to perform exhaustive testing, top to bottom, every class and every method at scale. So if you have 10 million lines of code, it's very unlikely that you're going to be able to test all of those lines of code exhaustively. So we talked a little bit about common types of testing, so unit testing versus integration testing, manual versus automatic testing. And what we're going to do now is we're going to take a look at kind of the two different motivations behind testing, or how testing should be done. So the first of these is testing to specifications. This is black box testing. And basically it ignores the code entirely, and what you're trying to do is make sure that all of the functional requirements, all the non-functional requirements, and all of the use cases are covered. So basically what will happen testing to specifications is somebody will try to put themselves in the shoes of a user and try to use all of the different business processes that a user might need in order to perform their job. The opposite end of the spectrum is testing to code. So if you are testing to code, you're ignoring the specifications, and what you're trying to do is test all of the different code components to make sure that you're getting the expected behavior. So when I say ignore the specifications, that doesn't necessarily mean ignore the results of the specifications. You still need specifications to understand what you expect to happen. But what I'm talking about is ignoring the specifications in terms of using specifications to drive testing. What we're actually going to look at is literal pieces of code and not what the code is supposed to be doing. So there are obviously going to be benefits and challenges to both kind of approaches, and ultimately what we're going to find is that testing to specifications is basically a way of mimicking exactly what the business team is going to do when they perform user acceptance testing. So that's kind of a nice situation to be in, but testing to code is way easier for engineers because they are more familiar with the code than they are the specific requirements for the entire system. So at a high level, what you want is to test the code from the engineering team, and then as you progress to QA, and then from QA to the business team, you want to gradually start testing to specifications because members of the business team and end users are very unlikely to know or care what individual methods are doing. They're much more interested in knowing that the actual business case is supported correctly. So compared to testing to specifications, testing to code is obviously the easiest to automate. You might be familiar with packages like Selenium or something like that that allow you to automate UI testing. You can obviously perform automatic testing to specifications or black box testing with those kind of frameworks. But it is way easier to consider a unit of code and then perform a unit test on that code. If you are able to do both of these things, basically what you can do is you can test that the specifications are met, and you can test that all of the underlying units of code that contribute to support for that specification are good. And that means that you're shipping high quality code and everything is kind of okay. A big issue with testing to code specifically is that it assumes that everything earlier in the process of development has gone smoothly. So you are assuming basically that the design is correct, and you're assuming that you have the correct expected behavior from the requirements. And in some cases, like the slide says, these are huge ifs. You could potentially have a significant amount of deviation if you haven't been careful during requirements gathering or during analysis. So we mentioned briefly last time that it is virtually impossible to perform exhaustive testing, but it's often useful to kind of think about these things mathematically. So let's say that you have just a main method in a class in Java or whatever language, and that class has 20, or that method has 20 different variables, and each of those variables can take on 4 different values. In that case, you're looking at 4 to the 20 test cases, and you're looking at maybe 30 seconds to test those, which means that it would take more than 1 million years to actually test all those things sequentially end to end to end. That's kind of a hilarious example, but if you can think about like at scale software systems clearly have more than 20 variables, they have more than 4 values that they can take on, they have many more than one method and one class, and so you can quickly see that the testing effort for a large-scale app balloons way beyond the amount of time that is even reasonable for a software team to actually spend testing the application. So the thing that kind of comes to mind is if you were trying to build a banking system that has maybe support for approving loan applications, the person's name on the loan application should have no bearing on whether or not they are approved for a loan or not. And in fact, if it did have some bearing, you probably have a very messed up algorithm to understand how to approve loans. And so in that case, it doesn't matter what the values of that variable are, the behavior should always be the same. And so what we can see from this example is you can start collapsing a whole bunch of these tests down into smaller and smaller and smaller tests that actually test more and more and more of the application. We don't have to have a specific test for Bob and a specific test for Sue. We kind of can have a larger coverage with a smaller number of tests. And so what this is called is testing with equivalence classes. So if you've taken the theory class or if you've taken discrete or discrete 2, you are probably familiar with the idea of an equivalence class. Basically, it is that you have a whole bunch of elements of a set, and if the elements of that set are functionally equivalent, then you can say that set represents an equivalence class. So the most concrete, the best concrete example, you can think of modulus. So if you have something mod 2, which would be even and odd, then all of the evens and all of the odds can be considered equivalence classes because their modulus value is literally equivalent. The evens mod 2 are going to be 0, the odds mod 2 are going to be 1. So in terms of testing, what this means is instead of having to test every literal value that a variable can take on, we can actually just pick a value in each equivalence class, and then that collapses our need for testing from virtually an infinite or an uncountably infinite number of tests down to a more tractable number of tests. So if we think about this specific piece, this is C# right here, but this is pretty understandable code in general. There are basically an infinite number of test cases for this piece of code. We have to consider things like the specific list size, so that size could be from 1 all the way up to the maximal size that the architecture of the machine that you're running the code on will take. What happens if I vary this start index from 0 or from 1 all the way up to, again, the maximal integer that the compiler or the machine will actually support. You obviously can't take both of these virtually infinite sets and then try to exhaustively test each of those scenarios. This is only one method. So if you have 10,000 methods in this situation and half of those, you can obviously see that that's not a great situation to be in. Now, the good news is that you actually don't have to do any of that. And so this may seem extremely obvious, but you will see even in test cases for large systems, that people will come in and they will do a whole bunch of tests, and they will literally have a test for 1, 2, 3, 4, 5, 6, 7, and they'll effectively pick random numbers, not understanding that there is a much more regimented or structured way of picking what the test cases should actually be. So we can kind of walk through that as an example, asking the question, what should we actually be testing? So what are the unique or the mutually exclusive conditions that we actually should care about? So What if my start value is greater than the length of the numbers array? Then, oops, that's going to explode. We've actually identified a bug in this code. We should not have this situation, so that's a thing that we should certainly check, and we'll find that we need to do some boundary checking. What if start is the end of the array? We should expect to get a 0 back. What if it's a less than? As long as we can pick one of these cases, we should be able to assume that math is not going to change, right? As long as we pick one, maybe two of these cases, then we can work out exactly what the value should be. And then we know that all of the rest of them, be they a semi-infinite set, should also be fine as long as those 2 or 3 or a handful are fine. So instead of having an infinite number, and in a lot of ways as infinite as a digital set of things can be, we are actually only testing 3 cases. We're testing effectively the boundary cases, and we're checking the case that is the sort of maximal case. And in that case, you could actually write unit tests for those 3 cases. And instead of kind of randomly picking values to pass into the method for your automated tests, you can use these 3 cases to guide what those unit tests should actually be doing. So out of this, we find the most important aspect in a lot of ways is trying to be malicious in the way that you choose the test cases for your tests. So instead of trying to reaffirm to yourself how great you are, instead what you should be doing is trying to pass the craziest stuff that you possibly can to your methods and seeing that if you break, you can fix it immediately without somebody else finding your mistake. So like we did before, you find that boundary conditions, so conditions like if I pass in an integer that I know is bigger than the size of the array, those are the kind of conditions that cause the largest number of corner cases. They're the conditions that most commonly fail because of a lack of null checking or lack of boundary checking and things like that. So boundary testing is really, really important, and what we saw was one example. And so you could easily think about boundaries where you don't have initialized values inside of a class. So what happens if the class is set to null versus what happens if the class is set to a default instance of the class. What happens when a date is date min versus date max versus some date in the middle of the range. That kind of stuff shows you how powerful boundary testing is. You could have hundreds and thousands of years of dates. The ones that you actually care the most about are the first one, the last one, and some values in between. Not necessarily all the values in between. So this is an example of how to test a range of values, or this is kind of an example of how it's important. So in 2008, the minimum Social Security deduction from a paycheck was 0, and the absolute maximum was 6,324. So if you look at this, you can actually break this infinite list of decimal numbers into these 5 cases. If somebody passes me something that's less than 0, if somebody passes me something greater than the maximum, something that is on each of the boundaries, and then something that is what I refer to as the maximal case, or sort of the happy path, something between 0 and 6,324. So to look at that kind of visually, what you basically have is you have a lower bound, you have an upper bound, and you have these 3 intervals between. So this is some value of a Social Security that is expected in some ways. These are unexpected, and then depending on the conditions, the boundaries are also okay or maybe not okay. And so testing in each of these intervals and on the boundaries, you will have basically all of the different cases that you could possibly imagine. Now, this is not necessarily true of all boundaries or all ranges, because you could think about things like dates again, right? So if your dates they have a lower bound, they have an upper bound. Neither the lower bound nor the upper bound nor any of the three that you pick in the other ranges or the subintervals are leap years. And then suddenly your calculation does something with leap years, and you've missed that code path. But you can see that you kind of have to find a malicious case where this doesn't work. This is a really good starting point for how to test range. And what you can do is you can kind of extrapolate from there, right? So if you're testing a set, ultimately what you want to do is you want to test something that is outside of the set and something that is inside of the set. Depending on your definition of set, you might also want something that is at the very edge of the set, but you may not even have a definition for what that is. Basically what this is showing you is that you want to figure out a test case. If you have a list, you want to try things that are in the list and things that are not in the list. You want to try things that are easy versus things that are hard. You kind of want to force the tests into a dichotomy when you're trying to test membership. You can also do the same thing with a precise value, right? So if you are testing for a specific literal, you could test with that literal and then test without that literal just to make sure that both possible code paths are tested. And this is basically no different than a set, except you don't have all of these extra cases that you're actually not testing in this case. So if you think about what a glass box approach is for kind of exhaustive covering, glass box approaches look specifically at the code itself. So you could figure out if a piece of code is exhaustively glass box tested, if some unit test exercises every possible line of code in the entire code stack. This is basically impossible for a really huge project, and you don't necessarily know that you're testing all the different code paths unless you can actually identify all the different code paths and how they are expressed in the lines of code. So just testing lines of code doesn't necessarily mean that you're testing all the lines of code in the appropriate order. And so even if you exhaustively test every line of code, you could still be missing a code path and you could still have bugs in the system. So because code paths can behave differently based on state, so that is, you could have 1,000 lines of code and you could run those lines of code in any number of different orders. You kind of have to understand all of the inbound values and all of the outbound values for each of those lines of code to have a chance of kind of intelligently developing test cases that exercise all of the code. So in order to kind of do that, there are various levels of granularity for glass box testing. The first one is at the statement level. So this is the kind of weakest form of glass box testing. And basically what it means is that every statement inside of the system, every line of code, literally line of code, has been executed, but it doesn't necessarily mean that that line of code has been executed in a reasonable order. So there could be something that gets passed into that line of code that is different than the unit test, and the unit test obviously will not catch any of those use cases or bugs in any of those use cases. You also have branch coverage. So if you think back to computer organization, you can think about every branch, so every loop structure, every if, else, every switch. And what you can do is you can try to take every possible code path through each of those branch statements. And so this is significantly stronger than statement coverage, because what you're trying to do is you're trying to take into account all of the different branching structures in the application. One test will go down the first if, then the second test will go down the else if, the third test will go down the else, so on and so forth. But obviously this is going to become more and more and more involved as you have more branches in each of your methods. Path coverage is the strongest because what this is actually doing is it is taking multiple combinations of branches into consideration. So if you have two if-else statements in a specific method, the difference between branch coverage and path coverage is that branch coverage is going through each of the possibilities in each of those branch statements. Path coverage is going to go through all of the combinations of the first and the second inside of a unit of code. So path coverage is the most exhaustive of all of them, and it is the most likely to actually identify an issue in your code. Statement coverage is the weakest because it doesn't have any checking on interdependencies, and it is the least likely to find a bug. But at the same time, statement coverage is the easiest to implement, and path coverage is the hardest to implement. And in fact, path coverage is often not trivial to implement because you have to actually identify all of the paths, and the paths could be different based on the caller of the method, for example. So if you have method level testing, you have a bunch of inbound parameters into that method, you might have to understand what all of the callers are passing into that method in order to actually identify all of the paths. So most of the time when path coverage is implemented, there's kind of an understanding that there could be paths that are not readily identified, and it's kind of an iterative approach to understand if a test fails. Is it because it is exercising a path that doesn't make sense? And if a bug is reported, is it because the path that bug is expressed in wasn't actually part of the automated testing? So black box testing is the exact opposite of glass box testing. So rather than trying to go through every specific line of code, you actually go back to the use cases, back to the functional requirements, and you go down each of those and make sure that each of those is supported by the system, and each of those gives you the expected result when you exercise them in the application. So just like with path-based glass box testing, you kind of want to make sure that you have multiple people doing black box testing, because you could have many different use cases, many different ways to use an application, even if it's something as simple as a data entry form. There will be people who do the form out of order. There will be people who make mistakes that are different in the form, try to eliminate data versus trying to redo the form, that kind of thing. You definitely can find more bugs if you have different people testing using black box testing, because you will get the kind of human component to the testing. And you also want to make sure that the acceptance criteria for any black box testing is provided by the business team. There's a point where making assumptions about acceptance criteria for specifications can pose a huge risk to the project. And the reason is because assumptions will lead you to believe that a black box testing effort passes when it actually fails for a very minuscule reason that is not at all clear to the software team. So you need very clear pass and fail indicators for each of the use cases or for each of the requirements, and that kind of becomes a back and forth conversation between the client and the software team. They have to agree to some degree of black box testing, and then in that agreeing, the business team should provide you with these testing criteria. So ultimately what you want is you want to make sure that your testing is structured. So at the end of the last video, we talked about how random testing is not really what you want, because you end up testing things that shouldn't be tested. You're testing the most commonly tested things usually. People are creatures of habit. The other problem with unstructured or random testing is that you could have different levels of testing on different releases. What you want to do is you want to make sure that every testing phase in your development cycle has the same level of scrutiny. And if you don't have that, what you will find is over time, the later versions will have increasingly lower amounts of testing, and then you will end up with stability problems. Even though the application has been in market for longer, it has more people working on it, so it should actually be more stable. So structured testing gives you a way of ensuring quality for the length of time the software is going to be in service, which in some cases is decades and decades. And without structured testing, you can run into some serious quality issues down the line. You also want to make sure that if you fail a test, that you don't just stop at looking at the code. So if a test fails, it could absolutely be that the code itself is faulty, but it could also be that the expectations of the code have changed. So the underlying requirements have changed, or the specifications have changed, and because of that change, the test is now incorrectly testing the code. So if you are very reactionary to test failures, you could end up actually making the application worse because you're not reacting in an agile way to changes in the specifications of the application. If you find yourself testing and you can't actually articulate what the piece of code is supposed to be doing, this is a key indicator that you haven't been given enough information. So if you were to sit down and you were to look at a list of functional requirements and a huge software specification, it would probably be very hard to understand what are the fuzziest or the most unknown pieces of the specification. However, if you're all the way down at the code level and you're trying to write a unit test for a piece of code and you don't understand what the unit test should be testing, that is a great indication that you should go back to the requirement, back to the specification, back to the business team, and have them hammer out all of the inconsistencies before you try to write, or at least before you try to test what the software is actually trying to do. So in the last video for this module, what we're going to do is we're going to talk about some more concrete ways to prioritize testing based specifically on defect prediction metrics. So defect prediction is this kind of study within software engineering where people can try to predict what pieces of software need the most testing because they will be the most likely to fail. So we're going to look at some of the most common defect prediction metrics, and we're also going to talk about how those can be used to prioritize your testing effort. We're also going to look at non-execution based testing, which amounts to code reviews and kind of editing sessions, and we're going to talk about how code reviews themselves can assist with testing efforts, but they can also help with sort of cross-training and making your software team in general a stronger team, a stronger part of the organization. So thank you very much for tuning in to this video, and I will see you in the next one.